Hey, it's your boy Chill here. Welcome back to Chill. In this video, we are finally going to create our class that represents window instances. And this is going to be a real architectural tour de force, a big meaty bastard, as they say. So we got to jump right into it. But before we get into the code, we got to kind of figure out our plan. What are our goals for this thing? What are we trying to accomplish? Because that is going to dictate the constraints that we have to work with. So the first thing I want for this new system is I want a separate thread for a message pump. Every window, when you create a window, will have its own thread that is running the message pump. And that's great because it allows the game loop to run even when the message pump gets blocked. And it gets blocked with certain messages. It just doesn't exit until you've finished moving the window or whatever. That's a problem. It freezes your game. And it's also nice to offload that processing, and because you have a dedicated thread for the events, you process the events with less latency. And the interface for the function, for the Windows class, it should be free-threaded, allow different threads to access it. Very important, since you're going to have a different thread actually running the pump. We're going to have to put some, thread protection in there somehow. And I'd like for asynchronous calls as well. So if you have a call that's trying to, for example, get the position of the window, that can be asynchronous. You don't have to block until you get that information. You can do other things while the call is being processed. I want the ability to spawn multiple instances of windows in a single process, and that I want to explore that space, for games and stuff like that. You might have, instead of having a split screen, you could have one player on each monitor. Much nicer if you can do that with different window instances. It's not a space that I see exploited that often in games, AAA or indie. And I think it's interesting, but that means that you don't have, now you're not going to be able to have, single global variables for all of your Windows stuff. You have to actually keep it in separate instances and tack those instances to the different window handles on the Windows side of things. So, one very big one here, I want proper and correct RTTI. I don't want slippage between the construction of our Windows object and the actual window on the operating system side. When we successfully exit the constructor, then we have a window. There's none of this bullshit of, you got to call a separate init function. You got to check an error code. No, constructing means there's a window, and destructing means the window goes away, and that is tied one-to-one lockstep. And I want to keep the interface clean, just the usual stuff. So, okay, there is our goals. Let's get started. So first thing in our Win namespace, let's create a class for window.h and .cpp, new files. All right, so here's the basic window class that we are going to start with. Of course, it implements iWindow. You've got your constructor, your destructor, your data here. It's going to wrap a thread, and it is going to wrap the handle to the window. We have function here, which is handle message, that is overriding from iWindow. That's the thing that actually handles each individual message as it gets dispatched. And the message kernel is the kernel that is going to run on the thread. And that's the thing that is going to be pumping the message queue. Also, we want an interface here, getHandle. This should be part of the virtual interface. For now, we'll think about, maybe privatizing this later or whatever. But for right now, easiest just to make it so that clients can get the handle directly. So that means in iWindow, we have to add that endpoint. We get that pure virtual function in there. Okay, so now Windows should be no more errors. Let's look at the implementation here. Constructor parameters should be pretty self-explanatory. We need the window class that this is going to be templated on. We need the title of the window, the size of the window, and optionally we can specify a position. Otherwise, it'll just take the default position when it spawns. And we have to initialize our thread object by giving it a function to run, and that function takes in this because it's a member function. getHandle, self-explanatory. The message kernel, it just loops, calling get message, translate dispatch, the standard Windows message loop. We're not doing peak message, right? Because this thread is only responsible for handling messages, so it doesn't need to poll. It can just wait and sleep when there are no messages, ready to pounce as soon as one comes in. And that's more efficient. All right, so the handle message function here, the general body of it is you got a switch, and you switch on what kind of message you get, and you do something based on that. I also wrap it try catch because we don't want this kind of function here to be, leaking exceptions. If you recall, this function is actually being called from our thunk here, which is called from Windows, so it will not be happy if an exception gets out of here. So we should handle it here, we should log it, and anytime a message isn't handled by this switch or an error happens, we just defer things to the default Windows procedure and it'll do the standard message handling for that message. Okay, so where to start? Well, I think we want to create the actual window called the Windows API function, and the natural place to do that would be in the constructor. If we ask Copilot, it says, yeah, call create window, W in here, get your HWin, set it on your instance. And that's pretty normal, pretty standard. It's also completely wrong. Why? Well, we are pumping the message on a different thread than the thread that is going to be creating the window object, right? Because the thread that creates this creates a new thread here that is going to be pumping the message queue. And here's the thing about Windows. You have to create the window on the same thread that pumps its message queue. Those things are tied together. There's a strong thread affinity for these Windows API functions dealing with a window object. So we must not call create window in the context of the thread coming in here. We have to call it in the thread running this kernel. Interesting. And that doesn't just hold for create window. Basically, any function that takes a HWin, we should be calling it from the thread that is pumping the message queue, the thread that created the window in the first place. So I have a question from a guy here. Are Win API functions thread safe or no? And you scroll down and are like, yeah, they're thread safe. No, they're not thread safe. Yeah, it's thread safe. This guy here is giving you some good juice. He says almost anything that takes an HWin or an HDC must be called on the same thread where that HWin or HDC was created. Thread affinity. Where can I get accurate information about what functions are thread safe or no? There is no such information in MSDN ! Very true. You do not know which ones can safely be called basically from a different thread and which ones cannot. And so what people tend to do is just call them all in the same thread that creates the window. That's a problem though. We want to create in our constructor. It's a very difficult situation here, but essentially we must cause the thread that's running this function, we must cause that thread to execute any API functions on our H window. That is our goal here. And there are several ways to accomplish that, but one very good and powerful way is to have a queue of tasks. And then this thread pulls tasks off the queue and executes them. So then any thread can push on a task that does stuff with the HWin, but only this thread will actually execute the tasks. So that's why we created the generic task queue. So we'll add our task queue in here. I'm making it mutable because some of the functions that use this task queue, they won't actually mutate the object logically, only the queue. So I'd like to be able to control the mutability of this object myself customizably, and that requires me to make this task queue mutable. So that's great. We have this task queue. Now, if you remember from the previous video when we created it, this task queue has a mutex. It protects its access from multiple threads, but it doesn't have any signaling mechanism to tell the kernel thread when a task is in the queue, so when it should wake up. So normally what I would do is I would add a condition variable and you'd wait on that conditional variable. There's a problem here. We are also waiting on get message. We cannot wait on both of those. So we'll always be sleeping on one or the either, or we'll have to loop and poll. And I don't like polling. I like waiting and sleeping until something actually happens, event-based if possible, because that's the most efficient, that's the most clean. So we can't wait on a condition variable and the message queue simultaneously. What do? We use the message queue as our condition variable. We use the message queue as the signaling mechanism to wake the thread up when it has to process a task off the generic task queue. So in our constant section here, we're going to add a constant, custom task message ID. So in the number space of the identifiers for Windows messages, there is a region that is reserved for use by the user, and that starts at message WM user, and you can use, I don't know how many of them there are. Seems like all the ones past 0x0400 are open for use in userland. So we can define them to have any meaning that we want, and then when we get those messages, we can process them with our custom processing. So we will post this message whenever there is something in the task queue for the kernel thread to process. Let us add a helper function where we can dispatch a function, and that will be pushed onto the task queue, and a future will be returned from that. So we push something on the task queue, we notify, and then we return the future. So that means we need this notify function. All right, so what does the notify function do? So what your boy Notify does is it posts a message to the message queue associated with the Windows handle that we have. And the message ID is our custom task message ID. And if something goes wrong, we log an error and we're going to throw an exception. So the thread that calls this, which is not the thread running the message kernel, usually, that thread will post a message. It'll get an exception if something went wrong. It can handle that however it likes. This goes into the queue. Now, how does the message kernel process that? Well, when that message gets into the message kernel's queue, get message is going to wake the thread up and it's going to dispatch that message. And eventually that message will end up here in handle message. So we want to handle that message. So if we get that message, we are going to pop the task off the queue and execute it. And then we're going to return 0 because we've handled this message. We don't want the default behavior for that, which would be nothing anyways, because the Windows system isn't aware of these messages past 400 hex. And you might be saying, okay, Chili, now I know what we need to do. Now we can dispatch the create window function. We can dispatch that call to this thread and have it execute on, the kernel thread. And let me tell you, that is wrong. That is not right. I'll tell you why in a second, but first let's look at the body of the create window routine here very quickly. Again, I cover this in my hardware 3D series, so I'm not going to go into great detail, but we get a standard, top level window here. It has a caption. It has basic system menu with a close button. You cannot size this one. No special styles associated with it. We convert the desired client area size to the size of the window that we need to create. Get the H module because that is required for creating the window. And then we just, fire all those things into create window.ex. Now there's something here that I need to change. So these two parameters here, they are, the X and the Y. If the X parameter is this special value, that means that the Windows operating system will put your window wherever it thinks is best. Otherwise, it's going to use the values that you put in here. But we're actually changing things up here. We're going to be able to optionally supply a position. So we're going to transform it to get at the member X. So if position is set, this will transform it to an optional that has the value of X alone. But if it hasn't been set, it'll be an empty optional, in which case we just want the CW use default. We'll do the same thing for Y, except in Y's case, CW use default doesn't have any meaning, so we could just put a dummy value in there, 0. Okay, so here's the creation function. We get the atom out of iWindow class that we injected. Very important aspect here is LP void, our custom parameter that we can pass in. That's a pointer to the instance of this class. That is how we connect everything together. This is the thing that gets picked up in the WMNC create message in the L param, and that we end up squirreling away into user data. So we call create window. If it fails, this will be null, and then we say, hey, we failed. So we'll just log an error with the error code, throw an exception. So this function now, this code is fine, but the dispatching is not good. Why? Why is it not good? Well, the dispatching needs a Windows message queue to notify. But a Windows message queue isn't actually created until you create the window. So we've got a chicken and the egg problem in here. We need a message queue to get the window created, but we need to create the window to get the message queue. So what we do here is for the very first task that we post, we don't use the message queue mechanism, special case. We're just going to push it directly onto the task queue. Now, how do we notify this guy that it's time to process the task? So you could say, well, the first task is always going to be create the window, so we could just assume it's there and execute it. But what if this thread executes pop before we manage to get it pushed onto here? That's a bad race condition. We try to pop when the queue is empty and everything blows up. So it's no good. We need to synchronize. A very lightweight synchronization primitive that I enjoy using is binary semaphore. Allows one thread to basically just signal another one that it's time to go. So we'll use this one, and this is just a one-off signal that we need for construction. We set it to 0 initially, so in the non-signaled state. In the constructor, after we've pushed the task on, Copilot has the right idea, but it is exactly wrong. You do not acquire, you release. So you say, okay, go get him, Tiger. And then what we're going to do in the message kernel, we wait here until we get a signal that there is the task in the task queue, and then we execute that task. And then there you go. And after that point, all of the tasks will be signaled via the mechanism of the Windows message queue. Now here's the thing. Our constructor for window, there's two things that we want. First of all, if something goes wrong in this, we want to throw an exception from here. The guy who ordered the construction should be the guy who knows what to do when things go wrong. So what we do for that is we have this future we call get on the future, and that, two birds with one stone. First of all, if something goes wrong, we get an exception out of here, marshaled into the context where we can handle it. And secondly, we assure that we do not exit this constructor until the object has finished its construction. And this is a beautiful system here. This system of pushing a task onto the queue, we get to keep the construction code in the constructor, which is the place where you would expect it to be, but it executes in the context of the message kernel, and exceptions are marshaled into here, and we synchronize so that we're sure that when we exit the constructor, we have a fully constructed object. This is beautiful. Now for the window destructor, it's very simple. Because we have our message queue already, we can just use dispatch to dispatch that task. And dispatching a task looks like this. You capture the instance pointer, and that way you get access to hwind. And you just call the function destroy window on hwind. If something goes wrong, let's log an error. Don't throw an exception from within a destructor. Don't do that shit. And you're good to go. We're not even going to keep the future for synchronization because we want to synchronize until the kernel thread exits. So we're going to join on kernel thread, and that means that when we exit here, not only has this task been completed, but we have also exited the kernel and it can be safely destroyed. Now what happens when you call destroy window? Well, that will actually post a message to the message queue, or maybe it even sends the message. It calls it synchronously, I can't remember. But either way, we're going to do case wm destroy. And in here, we're going to do very standard handling, post quit message, which posts a special message to the message queue of the thread, not any specific window even. This is the error code that you wish to use for exiting. And we're also going to set our hwind to null pointer. We're saying, okay, we're done. We're going to be destroying this. So let's zero out the handle because it's not going to be valid anymore. And you return 0 saying you've handled this message. And after you return this, wm destroy isn't a message that happens when the message is, or when the window has been destroyed. It's just giving you notification it's going to be destroyed. After you finish this, it will actually start to destroy the window. And because we post quit message in here, this get message w, it returns non-zero, basically Boolean true, when there's a message to process, except if there is a quit message, it returns false, and that means that we will exit this kernel, which means that this will join, proceed, and the object can then be fully destroyed. Now there's one final key piece to this puzzle. When you click the close button of the window, the little X in the top right, that sends a wm close to the window, and the default handling of that will be to do destroy. But here's the thing. We don't want external agents to destroy the window out from under us because we tie the destruction of the window to the destructor here. So we don't want it to be able to be destroyed when we haven't destroyed it yet. So how do we handle that? Well, we handle this message specially, wm close. And the way we handle it is we're going to introduce an atomic, lock-free, thread-safe flag in here, closing. So when the user clicks the close button or something else happens, we just do closing is equal to true. So this just allows the window to notify whoever owns it that, hey, someone wants me to close, you better destroy me or whatever. Or do whatever you want. If you want to ignore that, maybe just make the window bing or something, you can do that too. You can do whatever you want, but I'm just letting you know. So that means we add another thing to the public interface here is closing. That's not part of iWindow, so we'll have to add that. That goes in here, very basic and standard, and then in window.cpp. We'll put that bad boy in here. And now we can notify the outside world that we're closing, but only when they destroy us does the window actually get destroyed. It doesn't get destroyed from out from under our feet, and so we desynchronize our lock on the resources. We never desync. All right, and here we have our minimal viable product for our window. We should be able to construct this, see it, close it. Let's give it a shot. So go to Window App, include window.h, and let's just create one of these bad boys. Just create a local window object. Now the window class, we know we already have that in our IOC container. So we create a window like this, and now we just gotta wait until the window closes. So we'll just kind of pull the window every 100 milliseconds. See, are you closing yet? No? Okay, then we'll just kind of go back to sleep. Normally this would be where, you're doing your game logic, your game loop, your rendering, and you just periodically check the window to see if it wants to die yet. All right, moment of truth number 1. Does it build? Okay, to be fair, this is my first time using the optional monadic stuff. Okay, this is slightly less cool, but has the advantage of not failing to compile. Great. So, second moment of truth. All right, so when we run it, we get this problem. Well, the window doesn't show up, which is a problem. Also, we don't exit, but we get a warning here. Cannot create a file when that file already exists. So this is an H result that we got out of the destructor of window class. What? Why are we destroying window class? It doesn't make any sense because it should stay alive until the end of the program. It's a singleton. Silly chili. We forgot to resolve that out as a singleton because the window class doesn't actually keep. So this is actually a little design thing that I think that we could improve upon. We can make sure that window keeps its window class alive, even if singleton isn't. That's a good learning lesson there. But let's try this again. Now with a singleton so the window class doesn't die prematurely. All right, so now we're not seeing the window class dying, but we're also not seeing our window, which is a little annoying. Okay, isn't it fun when the documentation lies to you? In the docs, it says for position X, if X is set to CWU's default, then it selects the default position and ignores the Y parameter. So that means that Y shouldn't matter if CWU's default is set. Here, we're setting CWU's default and 0. We get nothing. Okay, well, let's set this thing that shouldn't matter to CWU's default. We shouldn't expect any change, right? And now it works! Okay, so the docs lie. They do that sometimes. But anyways, now our window is working. And if we click the X button, it should all just exit out nicely. No errors or anything. Beautiful. Now let's have a little fun with it. Let's add something to the interface. So let's add the ability to set the title of the window. So in iWindow.h, we add another endpoint. Set title takes in a string for the title, returns a future. So you can choose, even though there's no actual return value from this, you could choose to synchronize and to wait until you know that this title has been set. Yeah, window.h, we override here, and the implementation is we dispatch a lambda. It's going to capture in title by value and also the this, and it's going to call set window text on our hwind with the C string of the title. And if something goes wrong, we're just going to do a warning. We're not going to throw an exception in this case because, I don't know. I mean, you could. It wouldn't be a bad idea, but at the same time, I feel like this is non-critical and maybe an exception isn't warranted. Your personal preferences on this one. So now in main.cpp, let's have a little fun with it. Let's animate the Windows title. So here what I'm doing is, every 100 milliseconds, I'm incrementing X and I'm cycling it between 0 and 19. And that value is used in here with std format to basically print a variable number of asterisks. So this is a formatter that formats something to a fixed width, and the fill character is set to be asterisk. And so it formats to a fixed width, but the width is also formatted. So this X value is injected into here, used as to how wide I make this format, which determines how many asterisks are being printed. If you're interested, you can look up std format. You can do lots of crazy stuff with it. Let's see what it looks like. Here it's not aware of future or string, so we're going to put those in there. Now it should be happy. And there you go. Now we have our title bar with the animated title here with all the asterisks in there. Very nice. And one thing you might notice is that I'm moving this, but it is not blocking this animation, which it would be doing if they were in the same thread, by the way. All right, now let's hook up our window implementation into our IOC container in here. Now I want you to be able to resolve out a window, but with parameters. So we need to make the ability of window to be parameterized. So in here, let's add in the struct IOC params. What other parameters here? Class, string, dimensions, also position. Whoops, wrong one. Should not be iWindow. We'll include a bunch of things that are referenced in here. And okay, so now this can be used for our IOC. Now let me do a fun experiment here. I might make this a utility, but basically I'd like to have the ability, like you do with optional, value or something else if it's empty. I want to be able to do that with shared pointer. So I might put this into its own thing in utility, but for right now I'll just experiment with it here. Yeah, we include window.h, and then in here we're going to register iWindows implementation. It is going to take in iWindows arguments, and in here we're going to use the class that was passed in, or if there was no class passed in, we will resolve one from the singleton. We'll use the name that was passed in, or main window. We will use the size that was passed in, or 1280 by 720. And when we use the args, the position that was passed in, optional, we'll pass that directly because window also takes an optional. So now let's have a little fun with it. We don't need singletons anymore. We don't need window, we just need the interface. We're only going to interact with the iWindow interface, not with a specific implementation. So I'm going to go pog crazy here. I'm going to include ranges. I'm going to add all my namespace shortcuts in here. And let's just create a bunch of windows. Let's create like 6 windows. So we create a placeholder range from 0 to 5. We transform those into windows by resolving iWindow. And we store that in a vector. And then what we're going to do is, as long as our vector of windows is not empty, we're going to erase any of them that advertise that they're closing. I'm going to call the destructor on those. And for all the remaining ones, we are going to loop through them, animate the title, and then we're going to sleep for 50 milliseconds. Let's do 10 windows just for fun. Whee! Here we are. Okay, we got lots of windows. Note that dragging any one of these does not block any of the other ones. They're all independent of each other. And yeah, I got a fun time now trying to close all these bad boys. All done. And when they all close, window, the program exits, clean exit. All resources are automatically cleaned. Nothing is left on the table. One final fun little experiment. We know that set title returns a future. So if we call get on that bad boy, we're now synchronizing with it. What happens? So now it has to wait for each one to complete before it calls the next one. And they're still animating fairly nicely. They're still in lockstep with each other. But if I, for example, click and hold the close button, you see it freezes them all. Very interesting because it blocks our message queue. Clicking on this actually only does it for a split second, but then they recover. So it's not completely blocking, but it is for the very beginning here. But clicking this bad boy, that's a game ender. There's nothing you can do there. It freezes the entire program. And now if we don't synchronize, if we let them all run freely, detached, you see there's no hiccup on any of them when I'm dragging. And if I click and hold the close button, that does freeze the window in question. This is there's no way you can basically get around this. But the other ones, they're not impacted. They're free to run as they like. And there you have it. There is our beautiful system. And I hope you agree, like this stuff, this is really nice. If I do say so myself, I've really done it this time. And it's just very beautiful. Lots of amazing properties, very nice, simple interface, and clean architecture. So last thing before I forget, I want to make sure that we actually hold on and keep alive our window class. I'd say, yeah, we capture it here. And we keep it in our member data, so you can never have the situation where the window class can die before the window does, even if nobody externally is keeping it alive. Very nice. I just love seeing that cascade of windows appearing. That's cool. But yeah, so that is this video, and I hope you enjoyed it. And if you did, do click that like button because it does help and it does give me encouragement to keep going. And I will see you again with some more chill.